Good morning, or good afternoon, or good evening, depending upon where you are in the world. This is Physics 412, and I'm the instructor. My name is Jack Ng, and my email address is yjng, my initial yj, last name Ng, @physics.unc.edu. And if you have any questions, please write to me at that address, at your convenience. And I would reply as soon as possible, at my convenience. All right, so this is the second half of the course on electrodynamics. And we'll be using the same textbook as the one that you used for 311, namely the book by Griffiths. And, but I should tell you that, well, so we'll be covering the second half of the book. I assume that you must have covered the first half, namely chapter 1 to chapter 6 of the book by Griffiths. And so, to go along with the lectures, which are going to be pre-recorded, I will send you lecture notes, my own lecture notes, which are written in quite some detail of what I will be talking about in the lectures. But once in a while, I might my lectures might be slightly different from the lecture notes, but the differences are so small that probably you could not even tell the difference. Now I will take the liberty of using my own lecture notes, rather than the book by Griffiths. However, Griffiths would be a very good reference book. And in fact, you should read the book by Griffiths also, in addition to the lecture notes that I will be sending you. Now, my lecture notes will cover about 65% of the book of the last. I will follow the textbook only 65% of the time, roughly, maybe 70%, something like this. And the things that I would like to derive results rather rigorously. And Griffiths is a very good book, but one thing that I disagree with him is that sometimes he does not go into rigorous derivation, and just mention something without deriving it. I abhor that kind of approach. All right. Now, for the exams, you will be responsible for things I talk about in the lectures, and also my lecture notes, and the problem sets. But as I said, Griffiths is a good reference book that you should have, you have already. All right? And I will not be following the order in which Griffiths talk about the materials. But I will try as much as possible to follow the order that he has adopted for his textbook. There will be 2 midterm exams, and those 2 exams will be, of course, take home, open book, but you'll be, and also, of course, there will be the final exam. And for the exams, you will be allowed to use only 3 things: lecture notes, problem sets, and the textbook by Griffiths. And you must not collaborate among yourselves, And this is, otherwise you'll be violating the students' honor code. And I do take the students' honor code very seriously. All right, what else I should mention? And there'll be a grader. I do not know yet who the grader will be, but I've asked for Mr. Joe Marisol, and probably he'll be the grader, I would think. And he'll be grading the midterm exams and the problem sets. I will be alone. I'll be grading the final exam. Okay, what else do I want to mention? Okay, so that's about it. Okay, so let's not start. Okay. The second half of the course on electromagnetism. Okay. We will start with chapter 7. Okay, the chapter on electrodynamics. It's a very exciting chapter. So we will start with this exciting chapter in electrodynamics, and we will end the course on another exciting topic, namely special relativity. Okay, and there you see why and how special relativity is related to electrodynamics. Okay, all right. I will start with a discussion of a certain system. Let's say that I have a charge particle, charge Q, and mass M, and let's say it's moving with velocity v. This is my v. Oh, where are the erasers? Take away all the erasers. With velocity v in the presence of an external force F. And also, the charge particle Q is also subject to certain resistive force opposing its movement. So that let's now write it down. Newton's law to write down. Mass times acceleration is force. Mass times acceleration is equal to the force, external force, and the resistive force opposing the motion of this charge particle. Since it is opposing the motion, just minus v and times a certain parameter gamma. And for convenience, I will put also mass in this expression. So this is the system that I want to discuss. All right, let's start with, consider the case F equals 0. So as to know how to solve this simple differential equation very simply. In that case, then I have, dv by dt. By the way, this is my arrow. Arrow stands for, of course, denote vector. This is equal to minus gamma v. So it is an extremely easy, solution. Easy differential equation to solve. So v is function of time is equal to the following certain constant. Let me call it v naught times e to the minus gamma t. So the gamma would have the dimension of the reciprocal of time. So it can be thought of some kind of decay time. And let me move this different exponential function to the other side. Then I have v e to the gamma t is equal to v naught. And so that if I take the derivative, d by dt, and the time derivative, then I would have the following: d by dt v e to the gamma t is d by dt acted on this constant, which is 0. So that it shows you that, in fact, it is a good idea to consider this in the, for f is 0 in the case that what we learn is that, in fact, it's a good idea to consider not v, but v times this factor. So that to do that, obviously, all we have to do is to take this equation and multiply by this exponential function, e times gamma t. And what do we have? Then we have, e gamma t, e v by dt is equal to minus gamma d e gamma t. And you can in fact put this to the last side. The two terms will combine into st by dt e to the gamma t v. When I have e given dt acting on v, it will be this term. When it acts on this, it would be bring down a factor gamma, and that would be put on the last side would be minus. So this is hence we can hint that. Let's go back to our original differential equation that we're going to solve. This one. And now let's multiply this whole thing by this factor. So that I have so then in that case I have let me divide out by the last term, so that I will have in that case this, as I said, multiplied by e to gamma t, and then, the divided by m, and then these two terms combine to be this, d by dt, e to gamma t, v, that would be equal to multiply the f multiplied by e to gamma t. By the way, let me just mention this. Namely that, I found looking at my notebooks constantly would be very destructive and it interrupts my train of thought. So I try not to use my lecture notes. And therefore, since there are no students around, this is a pre-recorded lecture, there will be no one around to tell me I've made an algebraic mistake. So there would be mistakes, algebraic mistakes, trivial, stupid sign mistakes, etc. But since you have the lecture notes, which I will provide you with, you should be able to locate those trivial, simple, not trivial, simple algebraic mistakes easily and do the correction yourself. And by the way, the best way to do is the following. Namely that I will send you the lecture notes ahead of the taped lecture. What you should do is that you should read the lecture notes first, and then to get an idea what that lecture will be about roughly, and then view with the lectures on video, and then after that you should go back to the lecture notes and step by step rederive the whole thing with the help of the lecture notes. Okay? All right? So this is now the equation that I want to solve. In principle, f can be a function of time. And let me, so the left hand side is a total derivative. And let me in fact, change the t to t prime. And let me now integrate over t prime from minus infinity time when the force is not yet in force, when the force was not yet present, to the time that do the observation in t. And the left hand side, of course, is a total derivative. And there are two terms. The lower limit here is t prime is minus infinity. E to the minus infinity, exponential function gives me 0. So that there will be no contribution coming from the lower bound, lower limit. And the only term is coming from this one. So that I have e to the gamma t v t. And that's equal to the equation over t prime from minus infinity to the time t. E to the gamma t prime f of t. Okay. So that the v of t will be equal to e to the minus gamma t times what I have capital all the time. And t from minus infinity. Now let's consider the case that the force is in fact a constant independent of time. So let's consider this case. And also, for convenience, it turns out that it is convenient to divide out this force by the charge. So I divide by charge here and multiply by charge here. And let me, furthermore, multiply both sides by the charge q. So q squared. So the left-hand side is charge times velocity. Of course, this constitutes the current for that one single charge. And if I have the density of charges to be denoted by n, which is a constant, and multiply both sides by n, then the left-hand side would be charge to the one charge, current to the one charge times the density of charges. Then of course that would give you the current density J. And that is equal to now n q squared. Oh, let's see. I'm sorry. There's a factor m. I forgot it. Right. As I said, I tend to make seem naive, stupid algebraic mistakes. All right, so divided by m, and I can with force independent of time. So this constant, I can pull it out, and then all I have to do is supply factor of gamma here. You go along with this gamma, and then divide by gamma. So this is n q squared gamma, and then this thing. And let me denote this big F, the force, divided by charge, so it's force per unit charge by small f. You see why it's convenient to do so. Then I have F outside. And then here, the integration is very simple. Oh, I still have this factor. I will have to put it in a moment. Obviously, again, there's no contribution coming from minus infinity here. Oh, this is minus infinity to time t. The only contribution comes from this upper limit, and that will be e to the gamma t. But that will cancel to this e to minus gamma t. So that's it. Unless I have forgotten some stupid. Well, I think that's it. All right. So the RF for this system, J, the current density, is equal to this, which I will denote by whole thing sigma. So sigma times F. So sigma for this system, for this model, is given by n q squared over L gamma. This F can be anything. Okay. It can be, okay, in particular, F can be, okay, electric field. And it can be, in fact, okay, magnetic force. Which, of course, is you recall from the Lorentz force law, is speed times the magnetic field B. And this vector sigma is known as conductivity. So, okay, the current generated by a force F is given by that. So that, okay, the larger sigma is, for given F, the larger the current going around. So that sigma has the meaning of okay, how conductive the medium is. So that's known as conductivity. So then it is okay, large for conductors and small for insulators. In the book, there's a table okay, giving you the conductivity for the different materials. You can take a look. All right? So let's now, in fact, talk about the force per unit charge is electric field, E. In that case, the current intensity generated by this electric field E is equal to the conductivity times electric field E. This relationship between density J and the electric field E is, in fact, a form of Ohm's law. At this point, you may say, wait a minute, Dr. Ng, that is not the Ohm's law that I have come to love, to know and love. Okay. Ohm's law is the Ohm's law given by the potential given by I, the current, times the resistance. This is Ohm's law, right? But that's not that. You see, in fact, this is a generalized form of this Ohm's law. Therefore, I can call this Ohm's law also. Okay, so then now we have, so let me in fact copy down this result. Okay, and so what's the next thing that I would like to consider? Oh, I should give examples. Just to show you that, in fact, this is really Ohm's law. This is another form of this. Examples. I will talk about two examples, but the second one, very briefly, since it takes time. And it's just nothing but algebra, so it's simple stuff. I'll just tell you how to do what to do for the second example. But for first example, example 1, let's talk about a certain cylinder made of certain materials with conductivity sigma. And let's say that it is L units long. And that the two ends of the cylinder being maintained at certain voltage difference. So let's see that this maintain potential V and this maintain potential 0. So the question is, okay, what is the current that flows in this cylinder? I want to ask this question. Starting with this formula, Ohm's law, I will be able to tell you something about the current, which is in fact related to certain thing called resistance and the potential difference by this familiar form of Ohm's law. All right? What's I? You remember the current, this is J. It's nothing but current I per unit area. So that since the whole thing is uniform with area, let's say equals A. So the I is equal to J A. And J, as we know, is related to electric field E by this expression. So this is 1 over sigma, A, times the electric field E generated due to this difference in the potential. No, I just want to talk about the magnitude. So and if I divide out by L and multiply by L here, then the electric field E times the length, of course, is nothing but the potential difference. So that if I put this to that side, I will have V equals to I times L sigma over A. Oh, wait a minute. Wait, just a moment. Oh, sorry. Sigma is on top. Scare me for me. J is sigma times E. And multiply by L, so divide by L. So that's L divided by so that's sigma A is L. Now it's clear that we should identify this as the resistance of this cylinder for length L. Notice that the longer the cylinder is, the largest resistance. That is reasonable. But more importantly, notice that our resistance is proportional to the inverse of conductivity. That is to be expected. The larger the conductivity, the smaller the resistance. And the smaller the conductivity, the larger is the resistance. So that's reasonable. So that, in fact, it did. Starting from this, I've been able to get, for this example, cast the result in this familiar form of Ohm's law. This is the first example. And now let me use. By the way, I've talked about this system. So that the end results that I got an Ohm's law in the form of current density times conductivity times E. So that you can follow so the sigma is related in this system to the charges density and the coefficient of resistance force and mass of the charge in this manner. So that you can take this as a model of conductivity. And later on in the course, I will come back to this model and generalize it a little bit to get to do some interesting physics. All right? So now I should, my y-pass space is limited. Okay, I don't think I need this anymore. Okay, so I can erase this. And talk about the second example. And I would do this second example only very, very quickly and without giving you the details. Example 2. Let's talk about two cylindrical shells. One with radius B, and that's a coaxial cylindrical shell. Inside this big shell, let me draw by green color. Of radius A. And let's say that the two cylinders are maintained at a certain potential difference, V. So let's say that V on the surface of the smaller cylinder and 0 on the bigger cylinder. And we'll be interested in the current that flows between these two cylinders. So let's say that on the smaller cylinder, the inner cylinder, there is a uniform distribution of surface charge. Okay, and what do I use? I need to be consistent with my. Okay, so let's say that there is lambda charge per unit length. And let's consider a chunk of the system with length L. And we are interested in what's the current flowing for this section of the two coaxial mid-cylinders. All right? First of all, if that's the total charge, lambda, unit length on the inner cylinder, of course, that will give rise to electric field E pointed outside. So that I have a V at let's see, V at R equals A minus V at R equals P. That would be my V, and that of course is nothing but minus dE dot dR from A to B. R is the radius. Now, of course, we know that for this system, the electric field E at its point in the region between the two cylinders, but making use of Gauss law, draw a Gaussian surface, etc. So you know what E is. It's something times R hat. I use hat here to stand for unit vector. Arrow just stands for vector. So the R hat is nothing but R divided by the radius, the magnitude of of the radial vector. So that we know what this is. All right. Next, okay, we would like to make use of, okay, right. So now we're interested, let me again, okay, so we're interested in, oh, right, we're interested in the current that flows between the two cylinders. Okay. Current, of course, is nothing but the current density times the surface area. All right? And so you can imagine that this dA is nothing but area element on the surface of a Gaussian cylinder in between these two cylinders. And J, of course, is nothing but the little field E, which we have found, times sigma. Oh, I've forgotten that. Okay, the medium, the region between these two cylinders is made up of materials with conductivity sigma. So that's given. E is given. So this can be done. On the other hand, V, of course, is given in terms of this relation. And you know what E is, so that V can be found easily. And then you know the expression of I, you know the expression for V, then you will be able to show that, in fact, again, you recover the relation between I and V is in the form V equals I R. R, of course, depends on the geometry, depends on A, B, etc. And I would like to leave this as an exercise for you to work out. Okay, by the way, R's resistance, the resistance is measured in ohms. This is Ohm's law, after all. So ohms, 1 ohm is equal to ohm is in the unit of volt divided by current. So volt divided by current. Current is measured in ampere. 1 ohm is 1 volt per ampere. All right. So indeed, this is expression is as good a form of Ohm's law as any others. You may be familiar with this form, but actually this one is more general. Okay, let's now go back to this. Let's see. Have I erased this? Okay, let me go back to this general form of the current density related to the force per unit charge F. And now I can erase this and make this start the blackboard. And I have to make sure that I have to write between certain region, inside certain region, otherwise the thing will not be recorded. All right? So let's consider a certain circuit, closed circuit. And let's consider line integral of the force F dot dl. And this for this force per unit charge F, okay, going around this circuit. This line, closed line group is denoted by script E. And E here stands for the so-called electromotive force for this circuit. Electromotive force. And it is very often abbreviated as EMF. Now actually, this is not a force, this is a misnomer. After all, this force per unit charge and line equation. It doesn't even have the dimension of force, but this terminology got stuck. So we continue to use this as the electromotive force. Script E. Now, one important significance of this object, the electromotive force, is that it determines that the current I flowing in this circuit. And let me show you why that is so. So, all right. So let me know at this point. Should I consider this now at this point? Yes, okay. So the electromotive force is, let me copy the line group of force F. And the force F can be written in terms of the current density when around this circuit as J divided by the conductivity. And let's assume that this circuit has certain cross section with area dA around the circuit. So this is equal to line group of this, let's see. Oh, yeah. I thought I've erased it, forgot. J, you want to say what? J, the other signal, right. Let me, what should I do next? Forgotten. Let me take a look at this. Oh, right, of course. So that, J, you remember, is nothing but current I per unit area. So that I can write this as dL times I divided by this A. So let me use A, not the A. I is the same throughout the circuit. So that, now this has dimension of length divided by area divided by sigma. So this has the dimension of resistance, as you can tell from the first example which I've given. Length divided by sigma divided by area. So this is this electromotive force is nothing but I times R. So it's kind of voltage. And in particular, it determines the amount of current from the line. It determines I. That's the significance. All right. So that we shall also write down is in fact write down the expression in case I erase this. All right. Now, let's talk about this. Continue to consider this Ishimutsu force. How the Ishimutsu force can be generated. It can be generated by having batteries, etc. So this is, remember, this is nothing but form of voltage. A battery provides a certain voltage. And but this Ishimutsu force can be also generated by some kind of generators. And let us in fact consider a very primitive generator. And you see why we're interested in this particular discussion for the generator. And let me now use this sliding door. I should do model of generator. Let's say that we have a magnet, and that will generate a magnetic field. And let's say that, just for simplicity of discussion, let's say that that battery can generate a magnetic field, a uniform magnetic field B, going into the blackboard. B into. This cross here means into. It's uniform. And let's say that we have a shorted circuit in the form of a very simple geometry, a rectangular loop. With H. So, and it's put to the one side with velocity with speed V. And let me denote again. We call it here A, B, C, D. C being the point intersection of this blue line and the circle. D is this. And let's call the distance between A and B at this point to be small s. Now, of course, the circuit, there are charges inside the circuit. And let me consider a charge Q on this vertical line, part of the circuit. Q is moving with velocity V to the right-hand side in the presence of this magnetic field B. And you remember, that the force, magnetic force, is nothing but charge Q V cross B. V point to the right, and B goes into the blackboard. So V cross B would be F, pointed to the ground. So this is divided by Q, and we'll make take big F to the small f, force per unit charge. And now we know that it's pointed vertically up. And a charge on the horizontal line between B and C also would experience magnetic B. And the charges on this line AD also would be experiencing a force. However, the force acting on those charges being the same as the charge experienced by a charge on the vertical line. So that the force would be acting on charge here would be pointed up, so it would be perpendicular to this circuit. And I'll be interested in this line integral around this circuit. The line integral goes this way. If the force is perpendicular to the circuit, then of course the force that is there is zero. Since that force acting on the charge here will be perpendicular to the line integration. So the only contribution that will give the EMF to this system would come from the charges residing on this vertical line, AB. So this is line integral around you will take that loop. So this is DL times Q is gone. Q DL but V equals B. And as I said, the other contribution comes from the charges residing on AB. So the line integral goes vertically just along this vertical line from A to B. Times is VB. Of course, V and B being independent of L, of course, the integration is easy. So this is nothing but from A to B, the length is given with H. So V, E, H. So this is for this model of the motor force. The motor force is from E is given by this. Okay? Now the next step will be very interesting. Namely, let's do the following. Let's see. So this is a motor force given by rudder VBH. Let's consider, since there's a magnetic B, let's consider what's the magnetic flux through this circuit. And I will denote the magnetic flux by the symbol big phi. So this is the area integral of the magnetic B. The magnetic B is zero outside this rectangle, blue rectangle. So that would be the area that would be involved would be just the area in this part of enclosed by the circuit. So this is equal to E times S times H. Which, lo and behold, looks very similar to the expression for the motor force group E. Not quite. We have B, we have H. Here we have V, the speed for the motor force was for phi, the magnetic flux is S. However, it's easy to relate them. Namely that if I take a look at the rate change of the flux, that will be given by BH ds by dt. B is independent of time, H is independent of time. But S is, this is S. Since the loop's moving to the right, so S is decreasing. So in fact, the rate change of S is equal to the speed of V with a minus sign. since it's decreasing. So that d phi by dt is equal to minus BHV, lo and behold, okay, which is nothing but the BHV is nothing but the expression for the electromotive force. So we come to one important result. The rate change of flux through a circuit is given by minus the electromotive force for the circuit. This is sometimes known as the flux rule, law of flux rule. And by the way, you should also remember that there is this minus sign. So that if I put this minus sign to the right side, I would have the electromotive force is given by minus the rate change of the flux through the circuit. And this minus sign sometimes is people name it after Lenz. Lenz law says that that's a minus sign. The electromotive force, of course, is determines the current that goes around the current circuit. Okay, so that means that for a given circuit, the amount of current that flows in the circuit is given by minus the rate change of the flux through the circuit. So a tangent magnetic flux through a circuit generates an EMF which generates a current around it. And the direction of the current generated is given by this one side. It opposes the rate change of the flux. So sometimes you hear people say that, in fact, nature abhors the change of magnetic flux. Maybe, in fact, I should talk about an example, an interesting example here. Just to illustrate the importance of minus sign. And I will now erase all this. I don't think I need this anymore. This is just for particular models. I can use that too. This term. Example. This example is very interesting. It's very, very simple. And you might have done something like this in the laboratory. You used to demonstrate this law with the minus sign. The flux law. Means that let's talk about a certain solenoid. So that there's a current, taking the current around the solenoid. And inside the solenoid, there's a certain magnetic core used to magnify the magnetic field inside this solenoid. Is connected to a battery. It can generate current I. Let's put a certain magnetic ring on top of this long solenoid. start with, okay, there's no current, so there will be no flux through this ring. And then switch on the general current around solenoid, so there will be a current going around, so that will give rise to a magnetic field B, so that there will be a flux through this ring. And the flux will go from 0, when there's no current, to a finite amount of flux. And that flux is changing. Okay? So that we can apply this expression over there. If the motive force generated around the ring is given minus d phi by dt. Phi is the magnetic flux going this way, so that it is rising, but there's a minus sign. So that the electromotive force would try to oppose this rate change of flux due to this curve. And the way to do it is that it would generate a current on the ring itself that would give rise to a magnetic flux through itself, which opposes this rise in flux. So the current I induced on the ring with this goes this direction, opposite direction. If you think about the magnetic sign. And now notice that the current on the solenoid is this way, but the current around the ring is in the opposite direction. And now you remember from your study last semester, opposing currents repel. So that when you have current is 0 and it's switched on, once it's switched on, then the ring would be repelled from this solenoid, so that it jumps. So this is demonstration of jumping ring. And it shows the importance of this minus sign. All right. So next, let's continue. And what's now that I have Oh, by the way, I should point out one thing that's important. Namely, the Ryan rule. Rough here, the area element is dA, and dL is this way. So that in fact, if you go back the whole thing and go over algebra again. So dA is in the direction of B, this way, putting into the blackboard. Then your thumb putting into the blackboard. Then your fingers will be pointing along the direction of the circuit dL. So always use the Ryan rule to relate the direction of dL and dA. Through the next is a very important piece of physics, and at this point in the history of physics there came someone by the name of Michael Faraday. And Michael Faraday is one of the best, I think, experimentalists in physics, in the history of physics. He was not that well educated, but he was really a self-made physicist. And he had very good intuition. And let me go back to this model of generator. In this model, EMF is generated by a fixed magnet, generating the magnetic field pointing in the backward, and a moving circuit. So let me write this down. Stationary battery, but moving circuit. And we arrive at this result. And the whole thing about it is that due to the fact that the magnetic flux through this loop is decreasing. Because the loop is being moving out of this region. Faraday, microfaraday. Had a great intuition of thinking this way. He said, well, what's important is the fact that the battery and the circuit being in relative motion, so that there will be a change in the flux through the circuit. What if, instead of a stationary battery and a moving circuit, let's invest a moving battery. So the battery moves from towards the left, but stationary circuit. After all, Faraday had the intuition that what's important is the relative motion of the magnet and the circuit. So instead of a stationary battery, moving circuit, why not consider the other way around? Okay, fixed stationary circuit, but moving magnet. Okay. And before I consider that, let me tell you that Michael Faraday says something very, I think to me is very, very profound. And in fact, if you ever go to visit the UCLA, go to the physics building, and at one of the entrance doors on top of it is engraved the following line due to Michael Faraday. He says, nothing is too wonderful to be true. Nothing is too wonderful to be true. There must be some reason why something is true. All right, so let's see, okay? And so then now, what we have is this. Let me copy this one. One more time. Maybe I can do it here. I still 5 minutes or more. So what we have, stationary circuit, moving battery. Michael Faraday was not surprised to find out that, in fact, this flux law still obeys the same given by that. It's a force. Okay, but now you remember that the Higgs force is given by the line rule of force. And that's given by minus d phi by dt. And phi, of course, is nothing but the area rule of the magnetic field. For the case of stationary battery moving circuit, we find that there is a force, the magnetic force, given by this expression. But what about this case now? We have stationary circuit. So the charges on the circuit are not moving, unlike the previous case, right? They are almost with velocity v towards the right. Okay, in that case, okay, if the force is not magnetic, but okay, this rule still applies, what can this force be? What kind of force would that be? Exerted on stationary charges instead of moving charges. So you have stationary circuit and stationary charges. The only force that we know of that acts on stationary charges are electric fields. So that there's got to be some kind of electric field E. So that, now you have dl line of E is given by this. And let me rewrite this. It's minus the area integral of time derivative of E with respect to time. And here on the left hand side is line integral of the electric field E. And that I can notice that the right side is integral over area, but the left hand side is integral over line. They don't match. It would be nice if they integrate over the same kind of thing. It's not as hard as you may think. I can convert this integral of electric field E into area integral of its curl, if you remember Stokes' theorem. So let me write this as EA dot curl of E. And now you see that the two sides involve area integral. So that I identify, since in fact the whole discussion looks for, of course we have talked about a very nice regular circuit, a rectangular circuit. But in fact the whole discussion applies even when the circuit is arbitrary shape. And also one thing is that the manifold B doesn't have to be uniform. It could be arbitrary. It turns out this flux law still applies. So that since the integral can be applied to arbitrary shape, arbitrary geometry, so we identify the integrand of both sides to be equal. So that curl of E is equal, there's a minus sign, minus L E by L E. So that a time changing manifold B generates next an electric field E given by this. This was found experimentally to be true by Faraday. So accordingly, it is called Faraday's law. One of beautiful laws in physics and very, very simple. And I really believe that the true laws of physics, in fact, are very, very, very simple. I myself cannot do complicated physics. All the physics that I do tend to be very simple. I like simple things. But of course, it doesn't mean that simple things are true. Only the true things are very likely to be simple. Remember that. Okay, so this is Faraday's law in differential form, and this you see that is another form of Faraday's law in integral form, or this, or this. This is Faraday's law in integral form. And sometimes it's more convenient to use the differential form, sometimes more convenient to use the integral form. All right. And, oh, I hate the clock. It's almost time. I haven't finished what I want to talk about. see how much I can go, how much I should go. Okay, maybe I should finish up by talking about one simple example. I'll just write this down. Let's say that we have a region, a certain region, through which there is a maneuver B pointing vertically up, let's say, uniform. But it changes with the time. And let's say that that's the sentence here. A change in maneuver B, of course, would generate an electrical E. And the question is, what is the electric field E that got generated? Well, first of all, let us figure out what's the direction of E. And let's see. Okay. I'll come back talk about this in the next lecture. Name the thing, if instead of B, pointing this way, think of it as a current pointing up. You remember, a current pointing up would generate a certain current pointing in a circumferential direction. And that is the expression relating B to the current is, I will show you, is in the same form as that for the PHYS law. So that for this example, we know that the E generated should be circumferential. So that E would be E times circumferential direction. Right? And then, obviously, now you can apply the PHYS law in this way, in this. Namely, the line to go E is given by a rate change of the maneuver B. Let's say inside this imperial this R. So that the left hand side is the line integral of E plus E time E is in the differential is in the differential direction, and dl is this one. So that the integration can be easily done. So E times nothing but the circumference, 2 pi r. And that's equal to the rate change of the flux through this sheet region. Okay. And that is equal to minus, the area is pi r squared times dB by dt. And B is B naught here. So the E can be easily done. So this is a simple example. And in the next lecture, I will pick up a story from here. And you will see that PHYS law plays a very important part in the unification of electric and magnetic interactions. And the unification, as you see, is brought about by a Scottish physicist, and will come by the name of Maxwell. So we'll pick up the story from here next time. Let's stop here.